All right, so now we turn our attention to the cubic approximation. So just like we did with the quadratic, we're going to keep everything with the quadratic and just add a term on for a cubic term. And the question just becomes, what is that coefficient going to be? Well, if we went through and did our derivatives, we could see that P3 of A is going to agree, P3 prime will be F prime of A, P3 double prime will actually be F double prime. So we would like the third derivative, right, the third derivative to agree with the function as well. So if we did the third derivative of P3, right, we would like that to be F triple prime of A. So P3 triple prime of A. If we did the derivative 3 times, well, all these things are all going to go to 0. So that would be the derivative of that, be 3 times that stuff squared. Would be the first derivative, then you'd multiply by 2, and then you would actually multiply by 1. So we would actually have 3 times 2 times 1 times C3 has to be equal to F triple prime of A. So in other words, the C3, after we do the derivative 3 times, would have to be F triple prime of A divided by 6. Okay, divided by 6. But remember that 6 is 3 times 2 times 1, which is another name for 3 factorial. And that's important because later on, if we were doing it with a fourth power, something fourth power, and we were doing the derivative 4 times, we would start with 4, multiply by 4, then by 3, then by 2, then by 1. That would be 4 factorial. So the third degree approximation for this would be F of A plus F prime of A over 1 factorial, which is just 1, x minus A, plus F double prime of A divided by 2, but 2 is just 2 factorial, x minus A squared, plus F triple prime of A over 3 factorial, x minus A to the third. X minus A to the third. So that's our cubic approximation formula. Okay. And with that cubic approximation formula, we start to see a pattern, and we'll be talking about that pattern as we continue on. Here in a little while. But first, let's go ahead and use this cubic approximation. So let's compute P3 of x for the square root of x around x equals 1. So we've already done the P1 and P2 approximations. So let's now do the cubic approximation. So the only thing extra that we're going to need, since we already have the quadratic approximation there, right? We already have the quadratic approximation there, which we'll use, is we're going to need the third derivative of our function. So we got our second derivative, so we would do that derivative. So of course that would require us to multiply by -3/2 times the -1/4. Right? So what we would find here is that the third derivative, F triple prime of x, would be 3/8, and then we drop the exponent by 1, which would make it x now to the -5/2. So that F triple prime at 1 would just be 3/8. Be 3/8. And now we write out our expression. So the only coefficient I need is this 3/8. So f triple prime at 1 divided by 3 factorial would be equal to 3/8 divided by 6. Okay, and we would simplify. 3/8 divided by 6 would be the same as 3/8 times 1/6, which would be 3/48, which would actually simplify to be 1/16. Okay, so the third derivative evaluated at 1 divided by 3 factorial, that or coefficient for that term, will be 1/16. And then we just put it together. P3 of x will be everything that came before. So 1 plus 1/2 x minus 1 minus 1/8 x minus 1 squared. Now plus 1/16 of x minus 1 to the third power. 1/16 of x minus 1 to the third power. All right, and that would be our cubic approximation. And we can come back here, and I'm just going to do a quick little adjustment, call that y2 for the cubic approximation, or square root approximation. Now I'm going to come in here and do y3 is equal to y2 plus, and then I'm going to add on my last term, which is 1/16 times x minus 1 now to the third power. So I just want to zoom in here on the graph, and we can see the linear approximation, the green line here. We can then see the quadratic approximation, the purple line here. And now you can see the cubic approximation, which stays closer, even closer to the red graph for longer. Right? And it actually kind of maintains a lot of the structure. The graph is concave down here, and so is that graph. Now eventually it does lose on the concavity thing later on, because our graph is staying concave down, but the cubic actually does switch its concavity a little later. But it stays close to it. It stays close to it, and that's the idea that we're looking for, is that it should stay close to it. It should stay close to it. It's closer. It's a better approximation. And so you would expect, of course, that if we did another approximation, then it would be even better, and so on and so on. And that's what we're going to start talking about, is what if we did this many times, beyond 1, 2, and 3. How good would this look? Okay.